have a specific option within the tau makefile to generate the right output. So this is just an example of the kind of information that you can see in a Scholastica trace analysis. So it has these trees with the total execution time, and then it breaks it up for you into like the total time spent in MPI calls, and then out of those, the total amount spent in collective calls. And then it has a bunch of sort of it has a bunch of sort of common communication problems where when it analyzes the trace, it might notice that you try to do a reduce too early, or a broadcast too late, or you post or receive too late, and so the message is sitting there waiting, and it has no one to receive it, or vice versa, and or sometimes you send messages in the wrong order. So and each of these has, when you scroll over it, it comes up with information that describes what it's talking about with each of these different classes of issue. And so you can see it will classify for you, what parts of your code, how much of your code is having these problems. But then if you click on one of these, then in this view here, it'll actually show you the exact call in your, the function in your code that is causing the problem. And if you highlight that, it will also show you it'll show you the view of what's going on across all the nodes, which nodes are having that problem, and so you can isolate that, or if it's all just equally distributed, or if there's a hotspot. So the red indicating the hotspots. So you can. But since this is a call tree here, you can see that we can isolate this. Again, those are the same two functions that we saw in the profile, right? That this multi-body call, which calls this MPI, this MPI barrier, and this multi-body function are causing this hotspot. So anyway, so you can see all those things, but they're automatically analyzed and makes an attempt at making this more user-friendly. Okay, so I think we've run through most of this initial slide set. So just some things to kind of pull out of here. These are the take-home messages. At the very beginning, we talked about that the good choice of algorithm from the beginning is the most important thing. But then performance measurement may help you realize that you need a better algorithm, or it may help you to determine if you've implemented the algorithm well, if you know you've got a good one for what you want to do. There's just making sure that you've got that your code is running in serial before you do a lot of parallel performance profiling. So using your compiler optimizations, checking those out, and also we won't probably have time to talk about this much, but sometimes MPI parameter optimization is worth looking at some of those and trying that out for different types of codes. Especially if your code has irregular types of communication patterns, then you might want to, the defaults may not be a good choice there. And then there's a bunch of different tools available, and depending on what you want to do, then you can kind of look through and pick the right tool for the job if you just want an overview. Some of those sampling tools, or if you want to get an initial snapshot of where time's being spent, those sampling tools are very little effort with potentially high benefit, and so you can try that and then sort of know when to stop in this process for what you need. And then I guess one of the other final important points there is that on the TeraGrid, and also in other organizations like the TeraGrid, there are people who are available to collaborate with code developers and groups on using these things and getting these things embedded in your development process, or helping you get the most out of your code. So So on the TeraGrid, there's such a thing as advanced support that you can apply for with a TeraGrid allocation. And you can say, I want to check out the parallel performance of my code and see how it's doing. And then someone who is familiar with these tools and with this process can start to work with you in that process. And that's how this little story about this unres code came about, is someone asking for advanced support. And then we worked with them for a little bit and were able to point out some things that they could then go back and use to direct their development effort to improve the performance of their code. Okay, so originally, so this is the hands-on that I think some of you have already been looking at. So just let me just describe this, and then I'll take some questions, and then if we want, we can go through some of these examples. I can show you some of the things I described in the slides, and we can do that together. But we do have so we've got some exercises to give you some taste of finding parallel performance issues in real production scientific applications. On Kraken and Ranger, it's this unres code that I've been talking about, but I specifically didn't show kind of the answers in this talk. But there's performance issues there that you can take a look at. And then on Queen Bee, for various reasons, I've got this other code for technical reasons. We've got this other code to look at, which is LAMPS, which is another molecular dynamics code, which I'm going to tell you a little bit more about later, actually, because there's some cool things going on with that relate to what we're talking about this summer school. So go ahead and take a look at those. These are there for you to I think it's useful to get a feel for what it is to do this in a real code versus just an example code. Example codes are good too, though, but you have some of those in the general exercises that Sean Brown developed for Jacobi and the MD. If you prefer, you can certainly take a crack at if you've developed your own there and you want to try this out on those, then feel free to use that on those to get a feel, and then go to these exercises or vice versa. The best thing would be if certainly if you have your own code and you want to try this out while you've got some people here who can help you out, then please go for that. I mean, if you've got your own code and you want to try it, then don't feel obligated to go through these examples. This is simply to give you something to try out if you're not ready to try to throw these things, or if you want to gear up before you try it on your own code. But I certainly encourage you to do that, and I'll be available to help out with that during some of the time we have today to work on these things. So I think with that, yes, I'll stop talking and see if there's questions, and we can take it from there.
Question from Inkar. There's still that permissions issue with the makefile for tau on Ranger. Could you update that real quick?
Certainly, yeah. I did fix something there, so yeah. Let me. After we get done talking here, then I'll go and debug that.
Any other questions?
Question for Nancy?
Go ahead.
Go ahead. I was curious, I know in the past I talked to some tau people, and they're trying to get the use of PAPI incorporated into the Linux kernel, and we sometimes have issues with our admins don't want to put in an unvetted Linux kernel, so we can't really get access to all the PAPI counters and use of them. Do you know anything more on the status of will that be incorporated into the Linux kernel, the patch you spoke about?
I haven't checked the most recent news on that. The last news that I heard seemed to be not great news. I think they were. I remember being at a conference. This was actually, I think, now a couple years ago, where they had a big push to get that incorporated into the kernel, and then there was a decision made to not go ahead with that. And I know a lot of people were pretty, let down. So So that was the last I heard, and I think this. I haven't heard that the status has changed much since then. If someone here has more current information, then please speak up. My feeling, and this is something that I could go check, but my feeling is that it may still be a while. But
I have a comment about this issue from Penn State. As far as I know, after kernel version 2.6, as far as I know, PFM libraries has been the default performance monitoring libraries on Linux kernels. I mean, if you ever heard of a tool called perfmon or pfmon,
right.
as far as I know, yeah.
Right.
Actually, my question was going to be if PAPI is using any. Is it based on this PFM libraries on Linux, or is it a whole different library of its own?
You're asking if PAPI is using that?
Yes.
Okay. Yeah, I think I believe that there is something else to it. I'm not sure if I'm pretty sure it still requires a kernel patch to run PAPI, and so there's still an issue there. I'd have to go back and check on the details of what the dependencies are there. Yeah, I'd have to check on that. I think it's related to this pfmon, but there's more to the story there. So I'll try to check on that.
I have another question.
Okay.
Well, it might be a bit out of scope, but you told that the tools you have presented today, like IPM, PerfSuite, and Tau, are they specifically implemented for MPI and OpenMP applications, or can we use it with, for example, a pthread application?
Tau works with just about everything. So certainly pthreads is supported. There's actually that is one of the configuration options when you install Tau is you have to have support for pthreads in one of those Tau make files that I showed you a few times. So you got to make sure that it is compiled and configured to support pthreads and use a make file specifically for that. So yes, it will do that. So I indicated that IPM I don't believe is compatible with OpenMP, but PerfSuite is, and I'm pretty sure that PerfSuite also supports pthreads. So it varies from tool to tool, and I'm not sure about IPM. I've not used that one as much, but certainly Tau has support for pretty much everything. That's that's its thing. It does pretty much everything. And then so these other tools that I showed, there's your mileage may vary on any particular thing, but I'm pretty sure at least PerfSuite has the pthreads also.
Thank you.
Renzi question? Question from Renzi?
Yep, go ahead, Renzi.
So I'm reading through the instructions for Kraken, and it says the first one is compile the unres code, do a scaling study from 1 to 64 cores. I was able to build unres and run the qsub submit.sh, and I got that with just the submit.sh that was given, but then I tried to scale that up in terms of cores, and it seems to quit every time. I'm wondering what the magic numbers are for getting larger numbers of cores.
I see. I think maybe we should make that I guess I'd have to see kind of what's going on there. I mean, it should.
Okay.
Is there an error, or is it?
I tried one.
It just is the job gets submitted, but then it just.
It quits right away, or